Hi, boys and girls. All right, so the next part of our lesson for today is to start talking a little bit about distance over time graphs. And the important thing to know about distance over time graphs is that they're a line graph. And when I say that, I mean they're the kind of graph that looks like this. They have two axes or axi. I'm not sure. I know that last week in math you were working on plotting points on a graph, I think. But so that should probably help with coordinating what we're doing now. All right. This axis is called the y-axis, and this axis is called the x-axis. Now, in fifth grade science, we really only work with one quadrant, but when you actually see the whole coordinate plane, I'm using words that are new to you, coordinate plane, it really looks more like this, right? So the part that we focus on, and again, here's the y-axis and here's the x-axis. We're focusing on just, see, there's 1, 2, 3, 4 quadrants, right? So we're focusing on this part. Now, when you're representing data about anything, then you can represent it on graphs, and some graphs are better than others for certain things. But if you want to measure how often something happens, or how far something goes, or really anything that happens over a certain amount of time, then a line graph is your go to. So, what we do in science for fifth grade science is we assign the two different axes with representing different parts of the speed formula that you learned about in the first video. All right, so right here, we always put the distance on the y axis, and we always put the time on the x-axis, like always for fifth grade science. Now, when you are also measuring other things over time, it would still be the same way. And in our Zoom last week, when we were just sort of playing around with this, Kingston brought up a really good point, and let's go back and talk about that. He brought up the fact that if you're in the hospital and you are flatlining, right? Then you don't have any bumps on the graph, right? A flat line means that whatever you're measuring has just stopped. There's no heartbeats. So the flat line shows that time is going and passing. You can see that on the graph. Time is passing, right? But when you have a flat line on a heartbeat graph or a heart monitor, that means that you don't have any heartbeats. This would be labeled with heartbeats. Time is just passing, boop, 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 tick, tock, tick, tock, and you have nothing happening. So a flat line represents the fact that whatever it is you're measuring in time has just stopped. All right, so let's go back over to the slideshow. All right. And it says once you get good at reading a distance over time graph, you can quickly analyze your data to spot trends and make decisions about important real life problems. And it says that all data can be measured on a graph, or all data over all kinds of data. So, for instance, this one is weather data. And I know I'm down here, but do you see right here where it says years, right? And this is the change from the average temperature, and it's showing how over time from 1960 all the way up to like 1990, right, that the change from the average temperature has gone up, up, up. So this is actually showing weather data and maybe even a little bit of climate data, but showing that the average temperature, the change in temperature has gone up. So you can measure weather over time. You can measure precipitation over time, how much rain has fallen, how much temperature has changed. You can also measure the air pressure over time to see if you can spot any trends and how air pressure is changing. All right, this one is for population data. And can I move this? I'm trying to remember if I can move this. Oh, good, I can. I'll move me up here. So I'm not blocking the graphs. All right, this one shows the year is the unit of time, right? So it's still a unit of time, but then it's showing the population of a place. And so you can see that back at the year zero, over 100 years to the year 2050, the population is getting bigger and bigger. It was pretty flat for a while and not growing as much. But then once we got to around the 17 to 1900s, probably because healthcare got a lot better and scientists have learned a lot more about the human body, right? Then we've had a huge increase in population. All right, so that's kind of cool. It's also fun to look at the data on a graph and speculate as to why that data would be the way that it is. And notice we didn't have to look through lots and lots of tables of numbers. You could put all this information into like a T-chart where it says the year and the population, and the year and the population, year and population. But it's just really easy when you represent it on a graph because then you have a quick picture to show you how trends are changing. All right, health data, as I was saying earlier, right? So we know about the flatliner thing. If you're in the hospital and your heart stops beating, you've seen from medical TV shows, it just goes, and then everybody in the emergency room freaks out, right? They're all like, he's flatlining, he's coding. And then they go clear and they get the little electrical things, and they put it on someone's chest and they go, oh, it goes up in the air. And then if you're lucky, especially when you're watching a suspenseful show, you're watching to see if it changes from beep to bloop, bloop. And then sometimes people just flatline and die on shows, but a lot of times then the heroic doctor, right, brings the person back to life, bloop, bloop, and everybody's happy and everyone's high-fiving, right? Because the heartbeat had stopped over time. Time was passing with no heartbeat. All right, just think about it. All right, let's look at the next one and see what happens. Oh yeah, there's the flatliner right there. Poor dead person. They're having a perfectly healthy heartbeat, and then beep, time passes. And you can even see the grid marks, right? When we start doing our distance over time graphs, we'll use a lot of graph paper. It'll be fun. All right, look at business data. Right, so it's showing the time, which looks like it's in months. It's all of from the end of 2008 up to February of 2010. And it's showing, the game consoles. So way back in '08, right, Wii's were the bomb, right? And Xbox behind it, and then PS3s, which I think are we still using those? I don't know. I could ask all you guys, but I don't know. And then over January 2009, it flattened out, which means there weren't that many sold. And then all of a sudden, there was a huge spike in Wii's in December of 2009. Oh, Christmas time. That was when Wii's were the big thing, right? And then a gentler spike for right at Christmas time for the Xbox and the PS3s. But back then, everybody had to have a Wii, apparently. It seems like I remember that. That's probably when we got our Wii for the boys. All right, and then any data. This says the age in years. So here's the time across the bottom, and here are the number of teens. So this is teens with cell phones that live in small towns. So it's going from 13 years of age all the way up to 19 years of age. I wonder why 18-year-olds were less likely to have them. That's kind of weird. I wonder why. All right. And distance over time, most of all, which is what we're studying in here. All right. So notice that we have the distance on the y-axis, time on the x-axis. And then by the time we're done learning about this, you're going to be able to say, by looking at this, I know how this person walked, right? And one of the gizmos that you're playing with, if you remember, you're supposed to build the graph and then watch to see how the person moved. If you're really paying attention, you can start to learn some of the trends of the graph from playing with that gizmo. So continue to play with it. All right. And that is just to familiarize you with graphs. Let's see if I had, nope, that's it. And I think we'll stop right there for now. And goodbye. Love you. Be safe.